Okay, welcome to class. So before we get started, let me just start with our learning objectives, then we'll pick up where we left off last time. So today, we're going to begin by finishing that demo of the rubber band. We're just going to finish talking about it a little bit, because that really, I think, ties together entropy and enthalpy and how they can drive reactions. We're going to go from having these two distinct concepts to one unified way of talking about them, and that's called Gibbs Free Energy, right? We'll explain that Gibbs Free Energy has both a theoretical component as well as an experimental component, and we'll talk about how you calculate each part of those. If we have time, we're going to actually calculate things like equilibrium constants for different reactions, and we'll even get to electrochemistry if we have time, describing how these are analogous to free energy and how you can figure out what species gets oxidized, which ones gets reduced, or in other words, which one gets corroded away and which ones get plated onto it, which is things that we care about as engineers. So to pick up where we left off last time, the last thing we talked about was this rubber band demo. So let's recap a few of the things that we learned from that one. Okay, with the rubber band demo, we answered the following questions. The first thing we answered, let's see. We asked whether or not the rubber band reaction of it contracting was exothermic or endothermic. And since it got cooler, it must have absorbed energy, so that was an endothermic reaction, right? The next thing we realized was we said, okay, it's spontaneous, meaning once you stretch it, it all on its own snaps back together, even though that's an endothermic reaction. That's not the common response, right? Typically, exothermic reactions are the spontaneous ones, okay? The third thing that we asked was, okay, for endothermic reaction, are bonds being broken or formed? And we remembered that when you pour energy into a system, it's because it's using that energy to break bonds, right? We then asked, okay, as it snaps back, that's an endothermic reaction that breaks bonds. What bonds are we breaking, right? So we decided those were van der Waals bonds. And then the last thing that we asked, and this is always counterintuitive, right? I accidentally showed you guys this time, so you guys all got it right. But normally, if you've got a rubber band hanging by a weight and you hit it with a blow dryer and I ask what's going to happen, 90% of the class says it's going to get longer. It's going to expand, right? But in fact, we saw that it contracted, right? So the question that I have for you to turn to your neighbor and sort of start discussing is, what's driving the contraction of your rubber band, right? So turn to your neighbor and try and understand what's happening here. Okay, what do we think? What drives that reaction? Why is it when I heat that thing up that it contracts? Any thoughts? Anybody feel brave? Entropy is driving the reaction. The whole point of doing this demo, because it's unusual, it's atypical that entropy is the driving force. It's easier to think of examples where enthalpy, right, the exothermic versus endothermic drives it. Now, that's the correct answer, but why? What do we mean that entropy is driving this reaction? How about this? Consider these two different states of this reaction, stretched out versus contracted. Is the entropy larger or smaller, in which side? Which one has the greater entropy, the greater degree of disorder? So stretched out is not actually. And the way to think of this is imagine your big bowl of pasta that you boiled, right? That pasta is in a bowl. If you were to grab that thing just at 2 spots and stretch it, what have you done to the chains? You're not breaking it, you're just sort of stretching it as much as you can. Yeah, the region between where you're stretching it, those spaghetti strands are going to line up. That's more ordered than not ordered, right? When you just plop this thing in a bowl, the noodles can go every which way. That increases what we call a configurational entropy. Configuration is just how many ways that we can have it exist, right? When you force it to line up, you don't allow it to have kinks and bends in that lined up region. Another thing is that when you line it up, you get these polymer strands that are now laying next to one another, and that can lead to the formation of van der Waals bonds, right? So let's draw those. I'm going to draw my polymers like this. Every time that there's a kink in that represents a carbon, right? Carbon we know is going to have, if it's single bonds, it's going to have 4 bonds. So I'm going to leave off all the extra atoms, but technically, yeah, these should have things like hydrogen on the ends, right? Hydrogen, hydrogen, until it has 4 bonds each. I'm just going to leave those off as shorthand. So what happens here is, at any given moment in time, the electrons on average might be half above and half below, meaning they're just uniformly around this polymer. But if you took a snapshot, you might have, for a moment, slightly more electrons on the top side of that polymer, right? Which would lead to then necessarily slightly less electrons on the bottom side. And so this creates a temporary small dipole, right? There's a slight negative charge, a slight positive charge. That slight positive charge right here can induce a negative charge in this one. This is called an induced dipole, which we read about in chapter 2. So then this becomes negative and this becomes positive. And as you do these induced dipoles, that creates that positive, negative, and these are small. This isn't like a full charge, and a full positive charge, full negative charge. It can be like a fraction of a charge, but it's still a difference, right? And this creates an electrostatic attraction, which we call a van der Waals bond, right? So when you stretch this thing out, you created bonds. And when I let this thing go, I have to break these bonds, and that's why it absorbs a little bit of energy and gets cool, right? Now the other way around, if this thing is stretched out, and I give it energy by blowing on it with a blow dryer, then I'm providing the energy necessary to break these bonds. And in exchange, these, instead of being stretched out like that, can coil up and wind up, and I can increase my entropy. So it's this fascinating example where entropy is driving this reaction, right? Entropy is what's driving the reaction from stretched out to contracted, even though that's absorbing energy to do so, okay? Are there any questions on entropy versus enthalpy? We're giving you really simple explanations in this class because they're useful to describe how materials interact with one another. You will see more rigorous treatment when you take thermo. Any questions I can answer? Entropy versus enthalpy? Yeah?
How would it change, or would it change if rubber band's not stretched? It's just in its relaxed position.
If it wasn't stretched, okay. So imagine then, if it's not stretched out, if I've just got a rubber band hanging, and I hit it with a blow dryer, I don't have bonds like this, per se, which come from stretching it out. There's other types of bonds, but these ones aren't there. And so I don't need to get energy from the warm air to break these bonds. And if it's already in its most relaxed state, then there's no driving force for entropy to cause it to contract further. So instead, at that point, that's when you see this happen. Let's draw it. At that point, you then see energy versus interatomic separation. And an elastomer is going to look something like this, where it has some average separation between atoms, and then you will see an increase in your average atomic position. So if it's unstretched, it will actually expand. But in the stretched state, it's going to contract because it wants to increase its entropy. So great question. It's a good test question. Okay? Other things I could answer? Okay, should we keep going? Could you explain right now to your neighbor what is enthalpy and what is entropy? Entropy is easy. Explain to your neighbor what is enthalpy. Okay, let me pick on Elias. Could you explain what's enthalpy one more time for us? So yeah, if we go back to enthalpy, yeah, you're absolutely right. Enthalpy itself is the total measure of energy. It takes into account U, our internal energy, plus PV. And more often than not, we're not talking about the total actual amount of energy. We're talking about the change in enthalpy. And that, if we do things at constant pressure, this term goes away, and it's just equal to dQ. It's the change of heat going in or out. And almost always that's related to bonding. So in this class, when I talk about enthalpy, the first thing I want you to think about, it's usually going to be related to bonding, right? So if there's an atom that wants to have 6 bonds, and I take one of those away, I've changed its enthalpy, right? So we're going to come back to that a lot this semester, these concepts, okay? All right. So we learned about the first law of thermodynamics last class. Let's introduce the second law of thermodynamics. And we're doing this really basic. The second law of thermodynamics is as follows. It says that the change in entropy, ds, S is our entropy, is equal to the integral of the change in heat, dq, divided by temperature. And this is always at least equal to 0, and it's usually greater. This is why if you've heard from physics or popular culture that the universe is expanding, right? The universe, like the total system in which we exist, is expanding because that's increasing entropy. The universe is not going to contract until it collapses on itself. If anything, it's going to do the opposite. It's going to increase entropy. So entropy is going to increase. The only way that you make something have entropy not increase is if enthalpy is driving it, right? So again, you have both terms. You can reduce the degree of disorder, right? I can take that rubber band and I can stretch it, right? And that made it more ordered. But it came at the expense of enthalpy, right? So you have to consider these two things together, right? In general, what can we say? We can say that reactions that increase entropy are favorable. Increasing entropy in general is favorable. That's going to make a reaction want to be spontaneous. Now there's some rules. Again, calculating the exact entropy is hard. Calculating change in entropy is easier. So let's do some examples. First off, as you move up in molecular size, so if you went from a small polymer with just a few chains, right? Like I drew those things that had 4 or 5 kinks. Compare that to one that has 50 kinks, right? As molecules get larger, entropy gets larger. That's because there's more ways that you can arrange it, right? I love rock climbing. I love it. And I have long ropes for canyoneering when I do big rappels. And if you have a 70-meter rope, right, there's more ways that it can get tangled up on itself than a 50, right? A 50-foot rope, for example. That's way less tangled than a 70-meter. The longer something is, the more it can get tangled up, right? So bigger molecules, higher entropy. Now what about phases? Phases, you go from solid to liquid to gas, increases entropy, right? Entropy. I can't remember what I wanted to say about bonding. I'll come back to that if I think of it. Dissolution. If you have something like salt, like my TA's having a cup over there, if we have time to our demo, we're going to show you a neat demo by the end of today, probably next class. But if you take salt and you put it in water, that sodium chloride, those two ions are going to dissociate, right? That reaction, going from a solid to a dissolved solid, increases entropy, right? Took two things that were stuck together, and when they're floating around in a liquid, there's way more ways of arranging them, so that increases entropy. And atomic mass, bigger elements have more electrons, meaning those electrons can occupy space in all sorts of different ways, so they have greater entropy. So let's do some quizzes. With those general rules in mind, let's answer some questions. By the way, a quick note about the reading quiz. One of the questions was tricky. It was basically like, if the delta G is less than 0, is it spontaneous? I'm going to give you credit no matter what answer you put on that, because we didn't quite have it in the reading. We didn't quite get to it, so don't sweat it. You're going to get credit if you put anything there. Okay, this first question is as follows. It says calcium carbonate reacts to form lime, right? If you're like limestone, calcium carbonate is limestone, right? You've got your CaO, which we call lime, calcium oxide, plus CO2. So you have a solid reacting to form another solid and a gas. Does entropy increase or decrease? Okay, so get your answers in pretty quickly. Okay, just another few seconds. Get your answers in. If it's not working, you can just send me an email after class. Yeah. Okay, make sure you send me an email and I'll get you your credit. Okay. Okay, I'm going to close this poll. If your laptop's ever not working or something, just let me know in class and I can make it right. But I'm going to close this poll. Okay, entropy is definitely going to increase. Yeah, you went from a solid, which is a really compact way, to all of a sudden something that's a gas. That can be flying around the room in lots of different ways. That's way more entropy, right? Let's go to our next one. What about this guy? Silver as an ion, that's aqueous silver ions, plus chlorine ions, which are also aqueous. That means they're dissolved in water, reacts to form silver chloride. Is that an increase or a decrease in entropy? Okay, we're going to close the poll. Get your answers in. Okay, wrapping it up. So that's definitely going to be a decrease in entropy, right? Yeah. You took things that were able to fly all over the place in liquid and you forced them to come together. Decrease in entropy. Let's keep going. What about this one? You've got that molecule, N2O4, which is a gas, forming 2 moles of NO2, which is a gas. Is that an increase or a decrease? And tip here, remember our analogy. If I had a bucket full of white marbles, those things can be located in different spots. If I take those same marbles and I split half of them to be white and half one's red, does that increase or decrease the amount of disorder I can have in that bucket? Okay, we're going to wrap this one up. Okay, closing the poll. So again, it's going to increase it. If you can get multiple moles of gas, like an increase in the number of moles, that's going to be an increase in entropy. What about this one? A closed can of soda, or pop, or Coke, depending on where you're from, versus an open can. What does that do to entropy? Exact same thing, just pop it open. You don't drink it or anything, just pop it open. Your can of soda as an entire system, did entropy go up or down? Okay, we're going to close it. Get your answers in. Entropy increases. How come? You guys all got this right. What's the reason? You took carbon dioxide that was forced into a liquid dissolved phase, right? It was in a liquid phase. It was dissolved into the liquid. And you made it a gas. And that's way higher. That's the change in phase, right? Liquid versus gas phase has much more entropy, right? All right, how about these ones? You've got 3 molecules, CH2Cl2. So in all these, carbons in the middle, and carbon's bonded to 4 different things. You can have 2 hydrogens and 2 chlorines. You can have 3 hydrogens and 1 chlorine, or you can have 1 hydrogen and 3 chlorines. Which one of these has the highest entropy, or rank them in terms of order of entropy increase? Hey, there it is. I was looking for it. I left it here. Wonderful. Looking all over for that. Okay, get your answers in. Give another 30 seconds. Okay, I'm going to close the poll. Okay, what do we think? So 2, 1, 3 is the most responses. 2 has the most hydrogen, followed by 1. Yeah, so again, increasing with the atomic number, basically, of your elements. Chlorine's got more electrons, more configurational entropy there. Okay? That might be the last one. Okay, we'll come back to this in a minute. Okay, so any questions on these general rules for entropy? Okay, if not, let's keep moving. Okay, oh yeah.
So as each of those increases the entropy.
Okay, yeah. Each one, as these are written, going from smaller to larger molecules increases entropy. From solid to liquid to gas increases entropy. I can't remember what I meant by bonding, so I'm not going to talk about it. I can't remember what I was thinking about when I wrote that on there. Dissolution, as you dissolve something, it increases entropy. And higher atomic mass increases entropy. Yeah, so as written, those increase entropy. You know what I was thinking?
Was it when you have more bonds, you have more configurations for the things to bind those bonds to like vibrate and...
Oh, this is probably what it is. Which one has greater entropy, a single bond or a double bond? Does it? A single bond, if a system, like let's compare two things, right? Let's say that you've got this guy right here, right, which is bonded to different groups, versus this thing, which is bonded, right? What is the difference between these? First off, the number of things it's attached to, that favors the single bond because there's more of these side groups, which are going to do side group things, right? But there's another reason why single bonds are better in terms of entropy. In the back, what do you think? Yeah, a double bond, and you would have maybe seen this in chemistry. If you don't remember it, don't worry about it. But a double bond can't rotate. It's got like two struts, right? Where if you had like a single thing, it's like an axle that can spin. A double bond doesn't rotate. It's fixed. And so if this thing can rotate, imagine all the different entropy configurational arrangements you can have. That's probably what I meant with that. Thank you. Okay. Well, more bonds, yeah, in general, you've got 1, 2, 3, 4, 5, 6 here, and we've got 1, 2, 3, 4, 5, 6, 7, so there's 7 bonds, but it's more that the degree of, to be able to rotate that, I think, contributes much more to the entropy. Okay, I'm going to get rid of that. Now let's talk about something called Hess's law. Hess's law is as follows. It says that the total entropy and enthalpy changes for a reaction are constant regardless if you do that reaction in one step or multiple steps. So let's say we start out with something like PCl3, right? Potassium chloride, whatever that is. It's in a liquid phase. And you're going to turn that into PCl5, which is a solid, right? So that has some entropy associated with it. We would call that a negative change in entropy, right? Because it's going from a liquid to a solid. That's probably going to decrease its entropy. But you can do this reaction in one step, just exactly how it's written there, or you can do it in multiple steps. Like consider this, for example, right? You could start out with phosphorus and add 3 Cl2s to get 2 PCl3. You could take phosphorus and you could add 5 Cl2s to make 2 PCl5, and you can take that last reaction. So what Hess's law says is that you can take different reactions and you can reverse them if needed. You can multiply them by a number if needed. But if you add them together and you get this same final reaction, then you can add up the enthalpies and entropies of the individual reactions. So let's do this one together because it's a little tricky. We want to get to this equation, right? And here's our 3 equations we have to start with. 2 phosphorus, 3 chlorines equals 2 PCl3. So 2 phosphorus plus 3 chlorine gives us, is it 2? Yeah, 2 PCl3. Right? There's one equation. And that has a delta H of negative 640. Delta H, that's change in enthalpy, equals negative 640. Okay? Let's do another one. 2P plus 5Cl2, 2P plus 5Cl2, that's going to give us 2 PCl5, right? And that's got some enthalpy change associated with it. It is equal to negative 887. So real quick, and those would have units. Those would be kilojoules per mole. I ran out of space, so I'm leaving them off. But those have units. It's kilojoules per mole of substance transformed. So quick question, if we were only considering enthalpy on those two reactions, are they favorable? What does a negative number mean? Does that mean endothermic or exothermic? So exothermic, that means that these, as written, from an enthalpy-only perspective, you'd say probably going to happen, probably spontaneous. We haven't considered entropy, right? Just enthalpy right now. Okay, then this last reaction says PCl3 plus Cl2 is PCl5. That's the one that's written up here. So the question that I have for you is there a way that I can rearrange these two equations to get this one up here? What do I have to do? Could I add those in some way or subtract those or whatever and get that top equation? Well, let's start by reversing that first equation because it's got PCl3 as a product and we want it as a reactant. So let's start by reversing this guy. So we could say 2 PCl3 gives rise to 3 Cl2s plus 2 Ps. Now because we reversed it, what do we have to do to our delta H? It's got to change its sign, right? You can rewrite chemical reactions, but if you do so, you're going to reverse the sign of your entropy and your enthalpy and your free energies, right? So that becomes now positive 640. What happens if we add these two together? As it is right now, if we add them together, that goes away with that. Phosphorus on either side cancels out, okay? We've now got 3 chlorines over here and 2 over here. So if we added these up currently, we would have 2 PCl3 plus 2 Cl2 gives us 2 PCl5. Any questions right now? Everybody see that? That I can just literally add those together? I just reversed one, made it negative, added them together. Now if we do that, we also add together our delta H's, right? One's now positive 640 plus negative 887. Let's add those together. And I get negative 247. So as it's written, the delta H for this reaction is negative 247 kilojoules per mole. But are we done yet? Does that look like the reaction we wanted up there? No, it's because we're doing twice as much. So we can turn that into that reaction up there by dividing this whole reaction by 2. That's going to make the 2's go away and we have a reaction. We also have to divide our delta H by 2. So we've done this problem for you. Go ahead and punch that into a calculator real quick, and then you're going to answer this question, which is the total change in enthalpy for that reaction is A, B, C, or D. I'll come back to this in a minute. So we left off with negative 247. I'm going to divide that by 2, and go ahead and put your answer in. All right, this is pretty straightforward, I think. Okay, pretty straightforward. Any questions? Anybody not getting it? I'm going to close the poll. Get your answers in. I feel sad clicking it when I see numbers still rolling in. Okay, I'm going to close it though, for real. That should definitely be C. Good. Okay. So that is Hess's law. Again, you could do that equation in one step, just as written. It's negative 247. But if I gave you information about the other 2 steps, you could switch them, you could multiply them by 2, divide them by 2, whatever you have to do, divide it by 3, whatever the number is, you do that to the enthalpy as well, and when you add those together, you get the exact same enthalpy or entropy change. I saw 2 hands, Miranda and then Anthony. Or Mariella. Mariella.
How do you get the 2 Cl?
How do I get 2 Cl2? Good question. You've got on the left-hand side, you've got 5 Cl2, and on the right-hand side, you've got 3 Cl2. So if you subtracted 3 Cl2 from each side, that's where we get that. Yeah, Anthony?
So what you're doing here is just, you're taking the 2 bits of information that you were given and you're just manipulating them to...
Yep, that is Hess's law. That's all Hess's law is. It means you can take these things, they're additive and multiplicative. That's really what it means, right? You can multiply by them, you can divide by them, you can add them together, you can do subtraction, and that's all fair game. Okay? So it's very common on a test question for me to give you a reaction that I want, and I won't tell you what its enthalpy is or entropy is, but I will give you 4 or 5 other reactions, and if you combine those in some way and then add them up, that you get the right one, right? Okay, so another question I have for you. I've given you these delta H's for these reactions over here on the right, but where did those come from? Where did these things come from? To calculate those, you can look in some tabulated values. There's tables out there that tell you, they're typically written as this: the standard enthalpy of formation or the standard molar entropy. That's what, like, the terminology they use for them. When they say standard and formation, what are they really saying? Well, standard means that it's happening in the standard state, which is 1 atmosphere, and usually it means room temperature, right around 25 degrees Celsius. Okay? That means if I want to know what these are for a high temperature, I'm going to have to look up a non-standard state value. But let's just think about standard state for a minute, just room temperature, right? Let's go right here. Like, this might have some. Okay, so this is Chemistry Wisconsin. They put together a table for us. It says selected thermodynamic values at 300 K is room temperature, right? Pretty close to it, okay? And so take something like aluminum. Aluminum as a solid, it has a value of 0 for its enthalpy change. It has an entropy value that's positive, and it has a change in energy of form. That G is Gibbs Free Energy. We're going to talk about that in a minute, which is also 0. So we need some rules to understand what's coming from that. First off, let's see. If you take something that is an elemental substance at room temperature, 1 atmosphere, then there's no change in enthalpy to get it into that state, right? So for example, aluminum is aluminum at room temperature. So there's no change in entropy to take aluminum and to turn it into aluminum, because there's no change, right? So there's no change in enthalpy. However, if I wanted to know what the change in enthalpy was for liquid aluminum at room temperature was, if you could do that, that would have a value, right? Okay? So if you have an element that's in its elemental state at room temperature, then enthalpy is going to be 0, right? Okay? So take, like, let's find another one, like bromine gas. Bromine gas at room temperature. Must be a liquid. It must be a liquid by default at room temperature, because that's where its delta HF is, right? So if I gave you a table, I could ask, of these different phases, right, of bromine, you've got bromine as a gas, bromine as a liquid, bromine as a monogas, right? Which one is its elemental state at room temperature? And you'd say, well, it's the one with 0. Br2, bromine must be a liquid at room temperature, which I'm a little bit surprised about. But I'm not going to doubt Chemistry Wisconsin's table, right? So the other thing is that if you have a reaction which has multiples of these things, you can you can figure out what the change in enthalpy or entropy is for the entire reaction with a simple equation. It's products minus reactants. Okay? I'm going to write this out with some terminology that you'll probably want to start using. I'm going to write delta. Give myself some space. Oh, something's happening. OneNote is sort of the best, worst option, I feel like, for writing things in class, because half the times it does this and stops working for a minute. And I have to take the battery out and hope that it works afterwards. And there we go. Thanks a lot, Microsoft, for that. That brief interlude brought to you by Microsoft. Okay. So I'm going to write delta with a subscript R. Let me clean this up so it's really clear. Delta means change. Subscript R means for the reaction. H, it means we're talking about enthalpy as opposed to entropy. And the little dot sign up there, the 0 up top, means that this is at standard state. 1 atmosphere, room temperature, right? So the change in enthalpy for the reaction at that condition, we can figure it out by taking the sum, that weird E thing is the sum, from math, you've seen it somewhere, right? Of the individual delta H's of formation at steady state of the product, and you're going to subtract that from the sum of the delta H formation at standard state of the reactants. So it's products minus reactants, okay? So for that equation that I've shown you there, 2 moles of ammonia, NH3, as a gas, we could look up that, and that would be our product. And we could look up our 2 reactants, which is 3 moles of H2 and 1 mole of N2, right? We could go to this table, and we could say, actually, I think I've got my next question. I think I have the values here. Okay, so if we are doing, okay, right here. On the left-hand side, this shows you delta H naught. So that's delta H naught F formation for individual components. The F just means it's an individual component as opposed to a reaction, right? For hydrogen is 0 because at room temperature, hydrogen is hydrogen gas, so there's no change in enthalpy. Nitrogen, same thing. But ammonia, that's not an elemental substance, right? So it has a value. You had to combine 2 things to get it. So there's the NH3 value. And then you got the same values but for entropy over here, okay? So the question I have for you is, for that reaction as given, solve delta HR, the change in enthalpy for the overall reaction, and the change in entropy. The only thing to remember is this equation, products minus reactants, and the only other catch is if you have 2 moles of ammonia, then you need to take that number and multiply it by 2. If you got 3 moles of hydrogen, take your number and multiply it by 3, okay? So go ahead and give that a shot. Products minus reactants. Sum up the products minus the sum of the reactants. There's no way we'll get to this today, so you're fine. So if you've got it ready for next class, it'll be perfect. Did it work? Oh, should we show it anyways?
It works.
It'll just blink for like a second. Yeah. Red's a low voltage one. We might have that backwards, remember, too, right? Oh, yeah, you got it. LEDs only allow current one direction, so you got to make sure it's flipped the right way. Okay, you can enter answers. We'll give it just a couple minutes. Anybody feeling stuck? We got TAs that can help you. Just raise your hand if you are ever stuck in class. Okay, get your answers in, maybe one more minute. Okay, I'm going to close the poll. Get your answers in. If you don't know, take a guess. You get half your points just by trying. No one's panicking. I'm going to close it. Okay. People think, yeah, in fact, whoa, 27 and 2. Oh, there was D. It was probably D. I thought there was just the 2. Oh, could you not see D? On your devices, did anybody not? If you got that wrong because you couldn't see D on my screen, shoot me an email, and I will make that right. I forgot to scroll down. My apologies. Okay. Any questions on this, though, on calculating change in enthalpy, change in entropy for a reaction? If I gave you individual values, are there any questions about this? The only catch here, I'll do a question with one second. The only catch is that if I'm talking about a reaction that's, say, happening at high temperatures, but if I give you a table which is at room temperature, you cannot use these values, right? These values exist at a certain temperature only. I would have to give you values at that temperature of interest, okay? Now, Thomas, question? Great question. So that's a perfect question for our next section. How do you go from these values, which we can now calculate changes of entropy, changes of enthalpy? What is this concept of energy that I've been referring to over and over that we haven't actually seen yet, right? So this really asks the bigger question, if enthalpy and entropy can both tell a reaction to go one way or another, which one's actually going to dominate? You have to combine these two things together, and to do that, we have to have Gibbs free energy. It's written right here. G equals H minus TS. Who was Gibbs? He was the very first engineer, PhD in the United States. He was a contemporary of Boltzmann and Maxwell, of like the Maxwell equation of electromagnetism, of like the Boltzmann constant. He was their peers. He invented the field of statistical mechanics, which you guys will all take when you take thermo. He was a brilliant guy. Einstein called him the brightest mind in American history. I think he's a pretty rad guy. I'm glad that we named Gibbs Free Energy after him because free energy is pretty stinking important. It's defined as the maximum amount of non-expansion work that can be extracted from a closed system. That's kind of confusing. The main thing you need to remember is that Gibbs free energy is equal to the enthalpy of your system, that's a total measure, minus the temperature times the entropy, right? Now we can write some generic reactions. We can say the following. We know that G is a function of H, T, and S, but H itself, H was equal to U plus PV, right? So we could rewrite Gibbs as follows. We could say that Gibbs is equal to U plus PV minus TS, right? So it's really a function of all of these things. But it's also a function of N sub A, N sub B, N sub Y, and N sub Z. What are those? Those come from the generic reaction written as follows. Look at that generic reaction. You've got N sub A moles of compound A. That could be gasoline, right? You have Na moles of gasoline. Nb is a different compound. That could be oxygen. N sub B is how many moles of oxygen. Gives you N sub Y, that might be carbon dioxide, moles of carbon dioxide, and then N sub Z might be moles of water, right? So it's a generic reaction. It doesn't have to have two reactants and two products. It could be whatever you want, right? They just listed generic letters here. If you have that, then the number of moles will also dictate free energy, right? So this is really important. This gets to the heart of the fact that free energy has two components. It has a theoretical component, which is as it's written on paper, right? So let's go back up here. As it's written on paper, I could tell you what the Gibbs free energy for this reaction is. When you react nitrogen plus hydrogen to form ammonia, that has a Gibbs free energy theoretical component. But there's a totally other component you have to consider, which is the number of moles of these different things present. That's the experimental component. So theoretical and experimental. What this means is, let's say that this reaction is favorable, right? Nitrogen plus hydrogen react. Actually, let's go to our table. Is it favorable? Let's find out. D is the right answer, let's assume, right? I assume. D is the right answer, right? So we have our delta H and we have our delta S. Let's calculate delta G for that reaction, okay? Let's do so. Delta G for that reaction, let's give ourselves some space, right? Delta G is just going to be equal to delta H minus T delta S, right? We just took it straight from that. Instead of the absolute value of free energy, we're going to talk about the change in these energies. So delta H, we said, was negative 92.2 kilojoules per mole. Negative 92.2 kilojoules per mole. And then if it's at room temperature, let's say it's just 300 Kelvin, multiplied by what's our change in entropy? Negative 320. Is that right? I can't see that. Negative 320 joules per mole Kelvin, okay? Negative 320 joules per mole Kelvin. You have to be careful with you have kilojoules and joules that you get your units right when I add these things together. Let's go ahead and do it. I'm going to say 92,200. That's kilojoules into joules, right? That's a negative value. And I'm going to subtract 300 times negative 320, and I get for a value positive 3,800. So delta G for this reaction equals positive 3,800 joules per mole. That means since the change in free energy, we went from a lower state and we went up 3,800 joules, that it's not favorable. Anything in this entire universe that happens is because it goes down in energy. This went up in energy, so that reaction is not favorable, right? The formation of ammonia is not favorable from N2 and 3H2. Actually, to make it happen, you have to heat it up, right? Which we'll talk about later. That said, that's just the theoretical component, right? The experimental component says, even if this was favorable, imagine for a minute that this was a negative number. How do you know if that reaction will happen? It depends on the number of moles actually present in your reactor where everything's at. Maybe imagine this scenario. What if inside your reactor you don't have any hydrogen? Or if it's a tiny amount, then that reaction can't go forward, right? Even though on paper you said, oh great, it should happen, it's not going to go forward. In this case, it's not going to happen because the theoretical component says it's not favorable either. Okay, so a theoretical and experimental component, we'll bring those together in a minute. That's why G, free energy, is a component. It's a function of temperature, pressure, and all the different moles that are present. Now we need to define just a couple things. Since this is our expression up here, that's our complete expression for free energy. If we took the partial derivative with respect to temperature, and we held everything else constant, what do we get? Everything else is constant, what do we get? dg dt is just negative s, right? The partial derivative of free energy with respect to temperature, holding everything else constant, p n sub, I'll just call it I for all the different n's, right? That's going to be equal to negative s. Meanwhile, the partial derivative of free energy with respect to pressure, if we come up here, what should pressure be? If everything else is constant except for pressure, then the partial derivative is just volume, right? For temperature, n sub I, this is just positive volume. This means that the free energy, if you're changing pressure, like in this room, if I could keep the temperature exactly constant in this room, but I could suck all the air out of this room and lower the pressure, that the free energy change is going to be proportional to the volume of whatever it is we're talking about, right? This is going to come back next chapter, so we'll circle back to these. These become important next chapter when we talk about phase diagrams, okay? I'm going to skip that. Okay, so here's what I was just saying, that you have a theoretical component. I'm going to do that in blue. That's this guy. And you've also got this experimental component, which is that guy. The total change in free energy for a reaction, delta sub Rg, change for the reaction of the Gibbs free energy, which is what we really care about because it takes into account enthalpy and entropy, that has two components. The blue one, again, you could calculate it, and on paper it says the reaction happens or it doesn't. The second term says plus RT natural log Q, and Q is the reaction quotient. How do you know what Q is? Q is going to depend on what your reaction is. It's written as follows. Q, first off, it's equal to products over reactants. And it's equal to, if you're talking about gases, then it's equal to the partial pressure of component Z raised to the number of moles of Z, that whole thing, multiplied by the partial pressure of component Y. Component could just be like carbon dioxide, right? It's something that's in the reaction, raised to the number of moles of that, divided by the partial pressure of component A, raised to the number of moles of A, multiplied by the partial pressure of component B, raised to the number of moles of component B, right? So again, this is for our generic reaction of A plus B reacts to form Y plus Z, where you have n number A, n number B, and so forth for the different moles of your substances. Okay, that's your reaction quotient. Now, partial pressure, that's for your gases, meaning if in this room there's 1 atmosphere of gas, not all of the gas in this air is the same. Part of it's nitrogen, part of it's oxygen, part of it's other stuff. The partial pressure just says what's the fraction of it from a certain species, then divided by the total. And we are out of time, so we'll pick up here next time.